In the modern world, our lives rest on complex infrastructure. We rely on vast networks, power grids, transportation systems, and digital communication lines. Trillions of dollars are invested annually to build, maintain, and upgrade these assets. Advanced engineering principles guide design. Sophisticated financial models guide spending. The goal is simple: ensure reliability and safety. Yet catastrophic failures still occur, surprisingly often. These events are not supposed to happen. Systems are designed to prevent them. Models show very low probabilities. This creates a fundamental contradiction. On one side, an intricate risk management system, engineers, actuaries, financial analysts. On the other side, the stark reality of unexpected breakdowns and huge human and economic costs. Numbers and lived experience don't always align. Models say secure, yet structures fail. The puzzle isn't that failures happen, but why they happen despite sophisticated systems. It suggests a hidden logic beneath standard risk assessments. At its core, the infrastructure ecosystem is a complex web of interconnected actors, each with distinct responsibilities and motivations. The system begins with governments and public authorities. They often initiate large-scale projects and set overarching policies and regulations. Working alongside government are private and quasi-public organizations, utility companies, publicly owned or privately held, engineering and construction firms contracted to design and build physical assets. Financial actors provide capital for multi-billion-dollar undertakings. Investors, pension funds, banks providing loans, and insurance companies offering policies. A network of regulators and operators ensures the system's lifespan. Independent regulatory agencies provide oversight. Operators are the hands-on managers of the infrastructure, responsible for routine maintenance and emergency repairs. The journey of an infrastructure asset follows a well-defined, multi-stage life cycle, beginning long before any ground is broken. Once a project is approved, financing and procurement begins. This is followed by construction, the most visible part of the life cycle. Following construction, the asset enters its longest stage, operation and maintenance. One of the most frequently cited reasons for infrastructure failure is simply the passage of time. Many of the critical systems we depend on today were constructed decades ago, during periods of significant expansion. These assets are now operating well beyond their originally intended service lives, subject to the inexorable processes of wear and tear. Engineers conduct regular inspections to assess the condition of these older structures, using technology to find signs of degradation. The data gathered informs complex models that predict the remaining lifespan of a component and help prioritize repairs. However, attributing failures solely to age can be an incomplete explanation. While old age makes an asset more vulnerable, it does not preordain its collapse. The critical variable is not just the asset's age, but the history of its maintenance and the environment in which it is operated. Another common explanation for infrastructure failures points to the overwhelming power of the natural world. Hurricanes, floods, earthquakes. A power grid designed for a certain level of summer heat can be pushed to its breaking point by a record-shattering heat wave. Engineers incorporate historical weather data into their designs, but climate patterns are changing, making past preparations inadequate for future conditions. Yet, this overlooks the crucial role of human decisions. The choice of where to build infrastructure is a critical factor. Furthermore, the design standards themselves are a product of choice, balancing the high cost of building for worst-case scenarios against the perceived lower probability of those events occurring. This means that while a storm or an earthquake may be the immediate trigger for a failure, the underlying vulnerability was often created by a series of prior choices about location, design standards, and levels of investment. Beyond age and environment, the focus often turns to direct human error and mismanagement. This includes inadequate funding, deferred maintenance, simple design flaws, and construction mistakes. Chronic underfunding leads to a cycle of deferred maintenance. Small problems left unaddressed escalate into larger, more expensive, and more dangerous issues. In other cases, the fault is traced back to the asset's design and construction, where a flaw or the use of substandard materials can create a hidden weakness. These surface causes tell us what happened, but not why. Why was the maintenance budget cut? Why were corners cut during construction? Why was a known design risk accepted? Answering these questions requires us to look beyond these surface causes and into the deeper systemic pressures and incentives that shape human decisions. To understand why predictable failures occur, we must first look at the underlying incentives that guide the key players in the infrastructure system. For project developers and construction firms, the primary incentive is to complete a project on time and, most importantly, under budget. This creates a systemic misalignment. The entity that builds the infrastructure is not the same entity that will bear the full cost of its upkeep over its entire lifespan. This dynamic extends to the operators. Private utility companies are often incentivized by regulators to maximize operational efficiency and keep consumer rates low. The reward for a manager might be tied to meeting quarterly budget targets, not to the successful prevention of a low-probability failure that might occur years in the future. The cumulative effect of these disconnected decisions is an increase in systemic risk. The cost savings achieved today are not eliminated. They are merely deferred and transferred to an unknown point in the future. The consequences of these misaligned incentives are not isolated events. They create powerful feedback loops that can amplify risk over time. As this cycle repeats, the physical condition of the asset begins to degrade more rapidly. Minor issues cascade into more significant problems. The cost of addressing these accumulated problems now grows exponentially. What was once a simple, proactive repair now requires a major, expensive overhaul. This creates another critical feedback loop. As the physical risk of an asset increases, insurers reassess the probability of failure and adjust their pricing accordingly. This increases the operator's operational costs, further squeezing the budget available for maintenance and creating even more pressure to cut corners. The rational, short-term decision to save money on maintenance sets off a chain reaction that makes the asset more dangerous and more expensive to operate over time. Another hidden driver of failure lies within the very tools used to predict it: the mathematical risk models. These models are very good at predicting common events, but are far less effective at predicting rare, high-impact, black swan events that fall outside historical data. Furthermore, risk models often struggle to account for the interconnectedness of complex systems, failing to capture the risk of correlated failures where a single event triggers a domino effect. This creates a dangerous gap between measured risk and true risk. Decision-makers relying on these figures may develop a false sense of security. The system is then optimized for expected conditions, leaving it extremely vulnerable to the unexpected. The hidden logic of risk is also shaped by the vast web of rules and regulations designed to ensure fairness, transparency, and safety. Procurement rules often mandate awarding a contract to the lowest qualified bidder. In practice, this shifts the focus to minimizing upfront costs over long-term durability. Accounting rules also create a bias. Capital projects are often seen as an investment, while maintenance is treated as a cost that reduces profits, pushing organizations to build new rather than maintain old. Long, complex environmental and permitting processes can discourage proactive upgrades, making it seem easier to keep patching an old system than to navigate the bureaucracy for a full replacement. The failure of a single piece of infrastructure is rarely a localized event. In our deeply interconnected world, a breakdown can trigger a cascade of disruptions. This initial disruption quickly propagates through global supply chains. Manufacturers find themselves without critical components. The efficiency of modern logistics, relying on just-in-time delivery, makes the system incredibly fragile. A single point of failure can lead to empty store shelves, delayed construction projects, and lost productivity across multiple sectors. A physical failure of concrete and steel becomes a financial event, and the economic consequences are not distributed evenly. Large corporations may adapt, but smaller businesses are often hit the hardest. The cascading economic effects are mirrored by a growing strain on the financial systems. The insurance industry is on the front lines. As failures become more frequent or severe, insurers may raise premiums dramatically, or, in extreme cases, withdraw from high-risk markets altogether. This withdrawal shifts the burden to public finances, with taxpayer money diverted from other essential services to cover emergency response and reconstruction. Governments can become trapped in a perilous, reactive cycle of cleaning up after failures rather than investing to prevent them. The world of infrastructure risk is governed by two distinct logics: the logic of the model and the logic of the system. The model's logic is one of measurement and quantification. It creates a world of measured risk, providing a comforting sense of analytical control. However, measured risk is not the same as lived risk. The system's logic is one of interconnection, feedback, and human behavior, where small, rational decisions to save costs accumulate into large, irrational outcomes. The true story of infrastructure risk is not simply one of aging concrete or extreme weather. It's a system designed to optimize for short-term cost and efficiency, while inadvertently generating long-term systemic fragility. The challenge is not just finding more money for maintenance, it's about redesigning the incentives, regulations, and models to better align individual choices with the collective need for long-term resilience. Ultimately, this entire system is caught in a fundamental, unresolved tension: short-term efficiency versus long-term resilience. Immense pressure exists to deliver services at the lowest immediate cost. In a world of finite resources, immediate cost control is essential. But resilience requires investment in things that do not offer an immediate return: redundancy, higher quality materials, and preventative maintenance. How much efficiency are we willing to sacrifice for a greater degree of safety? How do we value preventing a future disaster against the tangible costs we bear today? There is no easy answer. How we navigate this conflict between the present and the future will determine the reliability and safety of the systems that underpin our world. You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.